Hello, everybody. Can anyone in any way hear or see me? Is it working? Oh, yes. Thank you very much. Yes, you can hear me. Can you also see the screen with the BI300 on it? Yes. And tell me what I'm drawing. What have I drawn? This is a test for you to see a heart. Yes, it works. And I think I figured out what the problem was earlier. Do you want me to tell you? Or do you think it's too embarrassing? I think the problem was that probably my internet connection wasn't good enough. And my daughter told me that she was watching a YouTube video, and I think that probably coincided. So, take-home message is, tell the family, including the dogs, the cats, and the tortoise, not to use the internet while I have a lecture. And I thought we are in the 21st century. Maybe not with Teams. Oh, really, Georgina? So it's not just me. That makes me slightly feel better on a Friday afternoon, evening. That's really good. And I better remove that heart because people might think all sorts of weird things. Oh, what a day. I think I say that every day, don't I? Huh. But maybe we get Teams sorted. And
So,
I thought I had muted everybody. Didn't I mute everybody? Let me see. So even that doesn't work. So who is not muted? See all. Aha! Ha! Ha!
So I can literally just unmute myself.
Yeah, I know.
I'm sorry, I just joined, that's why.
But I was told that that with a certain trick, you should be able to mute everybody. But obviously, Teams is Teams, isn't it? So please, everybody, mute yourself. And as much as I love the music, but please, please, please. Otherwise, everybody goes absolutely crazy. And I don't need crazy anymore. Not today. And I have to say, you guys have been absolutely fantastic. I mean, I would have expected far more of an est storm, because very clearly the technology is not good, but that's all we have at the moment. So I can only apologize. And hopefully at one point we will master it. Together we are strong. Maybe I believe it. So we wait another 5 minutes. Is that all right with you? Is there a module outline? Would you like a module outline for BI3? Well, for the part that I'm going to do with you, would you like that? Okay, I'll see if I can cobble something together over the weekend. Let's see if I get this sorted. How are you actually coping with all this asynchronous stuff, this additional things? Is it, I mean, some people told me that they find it quite confusing. Is that right? Mm. Okay. It might be a very stupid question. What would help you? So I can see here a checklist. And you want to know whether it's done before or after the synchronous. Would that help? Motivation, yes. Welcome to my world. I didn't say that, by the way. Checklist, yeah. Checklist would be nice. Mm-hmm. Yeah. Yeah, I can see that this might be useful. And yeah, we don't know what you need to know. Mm-hmm. Yeah, I think Konrad is a very good point. I don't have a favorite color. Any color is good. Yeah, I can tell it's Friday evening. I mean, who in their right mind schedules a lecture on a Friday evening? No, I've kicked them out. The dogs are not here at the moment. I kicked them out because they were eating bones, and God, it was noisy. I'm speaking facts. Oh, that's interesting. Well, I refrained from the alcoholic drink. Abigail, if you want to have a strong drink during a lecture, I'm not going to stop you. And I've got 2 dogs. Two dogs, 3 cats, and a tortoise. The tortoise, by the way, is called Usain, like Usain Bolt.
I think you're joking, man. Pretending about how you have to go on there. I know. No, I just stayed with him fucking tools.
Okay, and you are not muted. Thank you. No, Usain is in his little house at the moment. The Prophet Usain. I'll show you pictures. I promise. At one point, I'll show you. Actually, they usually feature in lectures. No, I didn't have a drink because I'm a total lightweight. And no, I'm not drunk. I had a coffee afterwards. But then coffee doesn't do anything to me, which is quite interesting, actually. And maybe I'm going to discuss that in the lecture with you. Oh, that's a good thought. Maybe I can do that. Let me just quickly check if I can do that. Discuss that in the lecture. Hmm. Hmm. That would be a good one. Yes, okay. Actually, I'm more or less teetotal anyway. Yep. Yeah, tea is interesting. Tea hits me. I can't drink tea later than in the afternoon. But coffee, I can drink a strong coffee before I go to bed, and it doesn't do anything. Usually, I have it in a mug. No milk, please. No sugar. I don't know why people dump cow juice into a nice infusion. That must be something British. I don't mean to be disparaging. Absolutely, yes. There's theobromine. How do you test for caffeine molecules? Oh, one. Yeah, we will come to that. Okay, shall we get started? Because I'm tired, you are tired, and let's get this done, right? So welcome to BI300, and hopefully this one goes better. I think it is recorded, as far as I can tell, and please don't forget to register your attendance in Moodle. People do contact me and say, oh, I forgot to register. Can you register my attendance for the lectures yesterday or earlier today? I don't have access to the Moodle attendance file, so I can't do that for you. So please make sure that you record your attendance. Otherwise, it gets lost. But at the moment, we are fully aware that it's not all working all right. So, hey, right. Yeah, don't worry about the registering as absent, not attend. Yeah, I think that's a good compromise, I think. Anyway, so BI300, Introduction to Biochemistry. Last time, when was that? Yesterday. Was it yesterday? Yes, must have been yesterday. I showed you how we can draw molecules. And the topic of this lecture today is we are going to talk about nucleic acids, or rather the building blocks. So the building blocks, and I try to write neatly, building blocks of nucleic acids. Okay. It was yesterday, yeah. Okay, good. Thank you. I'm losing track. So what we discussed yesterday was how you can actually draw structures. And yes, we are talking about nucleotides. So for example, we have some nice structures here. We have some ring structures here, and with a double bond, and so here's a nice ring. This actually, this ring here is actually a heterocyclic ring. So let me write that down, maybe a little bit like that. Heterocyclic ring. Heterocyclic because we have other atoms than carbon in the ring. So we have two nitrogens in the ring here. And that's why it is a heterocyclic ring in this particular case. Now, let's have a quick look at how the atoms are hybridized. We know that no, it's not a diamino. It is a hetero, because it's a ring. The official name is heterocyclic, and I will tell you in a minute what the official name for that is. So people in the BI300 chat, well, ask them to come over. I'm not doing BI300. We are BI300 now. Now, we have carbon molecules, and as you can see here, people are just simply too lazy to write the carbon, so they just simply write this here as sort of an edge or something like that. And when you see an edge, you know it's carbon. And well, a heterocyclic structure is just simply a ring that contains carbons and some other molecules like nitrogen here in this case. So whenever you see a sort of an edge like this one here, you know it's a carbon here, like that. And you know that carbon always has 4 bonds. Okay? So carbon always has 4 bonds. And you see that here. We have 1, 2, 3, and a double bond here. And we usually don't write the hydrogen. It contains carbon and a nitrogen here. Okay, so we usually have a hydrogen, but we don't write that. And what we see here is if we have 1 double bond, so 1 double bond, then we know that the carbon is sp2 hybridized. If we have a molecule like that, where the carbon has only sort of 2 lines shown, we know that there are 2 hydrogens there. There's no double bond, so 0 double bond, and therefore we have an sp3 hybridization. And we don't write it because it's just simply, it makes life so much easier. It's a skeletal ring, as you rightly say. Now, this molecule here, let's have a look at the nitrogen, because nitrogen can do a similar thing. And it can also do some kind of hybridization. And a very characteristic for nitrogen is that it can have a free electron pair. Carbon can't have that, but nitrogen can have a free electron pair. Now here, this nitrogen would be sp3 hybridized. And we know that sp3 hybridization leads to a tetrahedral structure. And therefore, this ring would not be totally flat. And therefore, I told you about when we were talking about aromatic rings, and I will do a YouTube tutorial about that. Realistically, the ring is not flat and therefore would not be aromatic. But the important thing is that because this is sort of a free electron pair, they are in the same plane as the p orbitals around the carbon, and they can overlap. And they can make this whole ring aromatic. So we have indeed an aromatic ring here, right? And that's quite important. Because the nucleobases that make up DNA and RNA are all aromatic rings. And as I said, I will do, and they are delocalized inside the ring. Absolutely right. Right? And we've discovered the aromatic stuff yesterday, but as I said, I will do a YouTube video for you guys so that you can have a look at it and do some exercises. Okay? Now, in the nucleobases, we either have one single 6-ring structure with 2 ends in the ring, and these are derived from the chemical compound called pyrimidine. Or we have a double ring structure where we in total have 4 nitrogens in here, and that is derived from purine. And we have actually the bases cytosine, thymine, and uracil that are derived from pyrimidine. So these are the pyrimidine bases, and I'll show you a picture of these bases in a minute. And we have the purine bases, adenine and guanine. And that's what I want you to remember. I don't need you to remember exactly the structures of these things, but I want you to remember that cytosine, thymine, and uracil are pyrimidine derived, and adenine and guanine are purines. How can you memorize that? There is the mnemonic cut pi. So cytosine, uracil, thymine are pyrimidines. Okay? Cut pi. And then there is this horrible gap U, G and A purine. I have a different way of remembering which one is a purine. I'm not entirely sure if I should tell you because it's a little bit naughty. Do you want me to tell you? But you don't tell anyone else that I said that because otherwise I get it in an egg. But the more outrageous a mnemonic is, the better you can remember it. So come up with okay. The way I remember it is all girls are pure and wear bras. Because a bra is a double ring system, right? So all girls are pure and wear bras. That reminds me that adenine and guanine actually are purine bases. That makes sense? Naughty things stick better. Absolutely right. It wasn't too outrageous. And as I said, they are derivatives of pyrimidine or purine. They contain nitrogen. They are heterocyclic or heteroaromatic molecules. They are almost flat. They are almost planar. And they absorb ultraviolet light around 250 to 270 nanometers. And next week in the BI300 module, talk a little bit about a spectrophotometry. But what it basically is that if you shine UV light, so UV light, into these purine or pyrimidine bases, they will absorb the light, and particularly at 260 nanometers. So they will suck up the energy of that light at 260 nanometers. And there is also a rule that when we look at, oh no, I tell you when we do the spectrophotometry. There is also a particular system for numbering the atoms. And for example, we always, when we number heterocyclic molecules, we always make sure that the that the non-carbon atoms, like the nitrogen, have the lowest numbers possible. So in the pyrimidine, we would give this N here position 1, and then we could go that way, or we could go that way. If we go this way, the next carbon has N3. If we went this way here, it would be 2, 3, 4, it would be N5. So therefore, we go this way. And in the purine, it's pretty much the same. We give we number it in such a way that the nitrogens have the lowest possible numbers. Does it make sense? So watch out, this guy here, that's the N1 in the pyrimidine. And watch out this guy here, that's the N9 in the purine, because they will be connected to other things. They are connected to sugars. So in adenine, we have that's the N9 here. And in guanine, it's also the N9. They are connected to sugars, and they make then up the nucleosides, I should say. In the pyrimidines, good thing that you ask. Again, in the pyrimidines, this is the N1 position. So here we have the N1. This is the N3 position. It's just the other way around drawn. N1, N3. Again, in uracil, which is the base that is found in RNA. It's not found in DNA. Thymine is found in DNA, but it's not found in RNA. And the easiest way to tell the difference between thymine and uracil is basically thymine just simply has a methyl group sitting here. Otherwise, it's pretty much the same as the uracil. So thymine is just a uracil, and it's methylated in position 5. So that's the position 5 here. And we have cytosine, which is where the oxygen here is replaced by an amino group. Okay, happy with that? Fantastic. I don't think I will ever ask you to write down the structures of the bases. I have to look them up, and I think life is too short to waste time memorizing structures that you can easily look up. So I'm not going to ask you the structures of these bases. Now, we said they are connected to sugars. And what are these sugars? These sugars are ribose or deoxyribose. And here again, for the question, the difference between uracil and thymine is this methyl group in at the 5 position. And uracil is in the RNA and thymine is in DNA. So you can, when you look at a nucleotide sequence and uracil is in it, then you know immediately that it is an RNA sequence. If it contains thymine, no, it must be a DNA sequence. Okay, so what sugars do we have? We really have only 2 different sugars. And they are both derived, or they are ribose and derived from ribose. Ribose is a 5 ring or 5 carbon sugar. 3, 4, 5, yes, 5 carbon sugar. And it would also be, this would also be a heterocyclic ring. Heterocyclic ring. Why is it heterocyclic? Absolutely right. It contains the oxygen in the ring, which obviously is not carbon, and therefore it is a heterocyclic ring. Is it planar? Is it flat? No, it's not, because all these carbons here, how are they hybridized? How are they hybridized? Vernon is absolutely right, yes. And the others are all right. It's sp3 hybridization, and therefore it's not a flat ring. And can this thing be aromatic, the sugar? Can this sugar be aromatic? Absolutely no, it can't be aromatic because it is not flat and it doesn't have any pi electrons in it, right? So it's not flat. One thing that's really important, and I just get rid of all these arrows here. One thing that I really, really want you to remember is the numbering. And that's really, really important. We start here with 1, and you notice in the bases we had just 1, 2, 3, 4, 5, and so on. In the sugar, we indicate the numbers by a prime, by a dash. So this one here is the 1' end of the sugar. This one here is the 2' part, 2' carbon. This is the 3' carbon. 4', and here, this carbon here is the 5' carbon. So the sugar has this dash on it. The sugar has this dash on it, this little, yeah, it's called prime. And otherwise we have the numbers. Usually the oxygen is not counted in any way. Does it make sense? So the nucleobases are just normal numbers, whereas the sugars have the prime. Sugars are prime. And we have modification. The primes is just this little, yeah, so this here would be the 1'. This would here be the 5' position. It's nothing else. This is the 2' position. And this prime just distinguishes the numbers from the bases. Because if there wasn't a difference between the numbers in the bases and in the sugar, if I said to you, this molecule is modified in the 1 position. You wouldn't know what I'm talking about. Is he talking about the base, or is he talking about the sugar? But if I told you it is modified in the 1' position, then you know that it is the sugar that I'm talking about. And the numbering is just simply by convention. One thing that we also have differences in is the deoxyribose, which makes up the DNA, and the ribose, which is the sugar found in the RNA. Right? Can you spot the difference? What's the difference between the deoxy and the ribose? Okay, where? Aha. The OH group, yes. And which position? Where is the difference? Where is the difference? Yes, Charlotte, absolutely right. It's the 2' position. That is the 2' position. In DNA, the OH group has been removed and just simply replaced by a hydrogen in the 2' position. Otherwise, there's no further difference between the two sugars. And for those of you who are interested, these sugars, these ribose, are actually synthesized both from glucose. Glucose is a 6-carbon sugar, and both of them are synthesized in a pathway, in a biochemical pathway, which we will discuss next term, which is the pentose phosphate pathway, or PPP pathway. And we will discuss that, how this is actually managed, going from glucose to a 5-carbon sugar, ribose, and then the next step is the deoxyribose. Okay? Happy with that? So I want you to remember that we have these nucleobases and we have the sugars. And in RNA, we have ribose, where we have an OH group in the 2' position. And in DNA, we have the deoxyribose, deoxy, D means without, oxyribose in the 2' position. And in the nucleotides, the ring is attached to the nitrogenous base via an N-glycosidic bond. Now, what on earth is an N-glycosidic bond? What is an N-glycosidic bond? N-glycosidic bond just simply means we have a sugar attached to nitrogen. And the nitrogen, as I said, in the pyrimidine is the 1 nitrogen. In the purine, it's the 9 nitrogen. And I want you to remember that. So position N1 in pyrimidine and N9 in purine. And this bond is really quite solid. It's fairly stable. And that is also why DNA actually is quite stable. DNA is pretty stable. I think scientists in Russia just isolated DNA from a mammoth that has died about 100,000 years ago. And in theory, for example, if you, for example, believe Jurassic Park, you could extract DNA from insects which were trapped in amber. So the DNA has the potential to be stable for millions of years. It's really extraordinary. So that's really an amazing molecule. And of course, we have another group of things that attaches to it. Here's just a quick slide which shows you how these nucleobases are attached to the ring. It's usually shown like that. So here you have got the nucleobase, in this case adenine. Here you've got, oh, what is this? What is the ring? What is the sugar? Is it deoxyribose or ribose? Ribose. How do you know it's ribose? How do you know it is ribose? Because of the 2' OH group. Absolutely right. Absolutely right. Now, this thing that can swivel around this bond here, so this would be anti-adenosine. It's in this position, it's sort of almost like a flag. Whereas in this position, it's called syn, but don't worry too much. I'm not going to ask you about that. Okay, so we have the bases, we've got the sugars, and the last bit that we need is something else. So let me just simply summarize that. We have the nucleotides. These are the building blocks of DNA and RNA. They consist of 3 components. It's the base, this guy here, that's the base. We have it attached to a sugar. And when we have base plus sugar, then this is called a nucleoside. Remember the S, nucleoside, sugar and base, right? The last bit that we need is a nucleoside plus phosphate gives a nucleotide. Remember the T, right? T means total, everything. Nucleoside plus phosphate. So this one plus this one is the nucleoside plus the phosphate. That is then the whole thing. And you can remember that probably the S stands for probably sign which is the Latin word sine, which means without. So without phosphate, right? So a nucleoside is base plus sugar, no phosphate. Nucleotide is nucleoside plus phosphate. And very often we have 3 phosphates here. But in DNA, these 2 outermost phosphates, or when we synthesize the nucleic acids, these 2 outermost phosphates are cut off. Now, very quickly, and I'll do that here, we have the sugar. Let me just simply remove that stuff here. Now, I want you to tell me, where is the phosphate attached to? The PO. Where is this attached? Ellie says 4'. I'm really grateful that you used the prime. That's great, because that shows me that you understand. It is actually the 5' end. So really note, we have this 5' end, and here, this guy here, that is the 3' end, right? And if you got that, then you are almost there when we're talking about DNA. I'm really, really pleased that you got that. So the phosphate group is attached to the 5' carbon. And what we actually have here, if you remember, the carbon, the 5' carbon, that looked like a little bit like that, OH, OH, H, and then here it went into the ring structure. If we have a carbon with an OH group, does anyone know what this is called? What is a carbon with an OH group? It's a hydroxyl, yes. And you can say both. It is, you can call it a hydroxyl group, hydroxyl carbon, or the more common phrase is an alcohol. So we've got an alcohol here, and the way it's basically done is an alcohol, oops, plus we have an acid, and in this case, phosphoric acid. So phosphoric acid plus the alcohol, what do we get? And that is for the chemists amongst you, people who have done more chemistry. What is this bond? What do you get when you add an alcohol and an acid? What do you get? Alcohol and acid together. No, you don't get a carboxylic acid. Yes, you get an ester. So this thing here is actually an ester bond. And esters have the property that they can store a lot of energy in them. So this is, if you like, a high energy bond. But you will do that in the chemistry module, so don't worry. It is an ester. And by the way, it's a really bad joke. It's a bad joke that all chemists call their daughters Esther. It's not true. I can confirm that. Nucleotides don't smell of anything. Not all esters smell nice. What you are thinking are fruit esters, for example, in banana or in, where else? Pineapple. They are very common esters, common compounds made up of an alcohol and an organic acid. And or strawberries. Oh yeah, strawberries have really nice fruit esters, but in DNA or RNA, they don't smell of anything, at least not for us. Yeah, and smell my nucleotides, I think that's a really cheesy chat-up line. Well, you can try it. Let me know whether... And yes, of course, they are used in perfumes, although esters have also the habit that they sometimes are not terribly stable. It does. It works. Smell my nucleotides as a chat-up line. Well, there's a lot I could say, but I'm not saying because it's Friday evening. So here is a little bit of a summary of what I've done. We've got the nucleotides. It's a nitrogenous base plus a pentose sugar, 5-ring sugar plus phosphate. Nucleoside is just the base and the pentose, no phosphate in it. Important, the phosphate is always in the 5' position. And we have this particular numbering. I'm not really expecting you to really remember the numbering. I'm not going to ask you that. I might ask you how is a purine base linked to the sugar? And then you probably tell me that it is an N-glycosidic bond, and the purine would be in the 9 position. And that makes me quite happy. And you see that here. So the purine would be in the 9 position here, and the pyrimidine would be here. And if I ask you what bond is between the phosphate and the sugar, then you tell me that this is an ester bond, and it is in the 5' position. Does that make sense to you guys? And you are absolutely right. A nucleotide contains both an ester bond and a glycosidic bond. Spot on. You totally nailed it. Right. Tell you what, I think we should call it a day. We had a long week, and we will discuss then DNA and RNA structure next week. But I'll send you, do you still want me to send you all an email about what we are going to do next week? Do you want me to do that? Yes?
Yes, please, sir.
Okay. When will this be on Moodle? So some people say no. Well, then you just ignore it. As soon as I have downloaded it, because I need then to upload it to Moodle, and that might take a few hours. I hope it will be up by, let's say, tomorrow lunchtime. Are you happy with that? In this case, have a lovely weekend. Go in peace, but please go. Enjoy your weekend. You worked hard. See you next week. Take care. Bye-bye.
Bye, sir.
Thanks, sir.
Bye, sir.
Cheers, sir.
Bye, sir.
Thank
What do
you.
you think, sir?
Thank you, sir.
Bye, sir. Bye, sir.
Bye, sir.
Bye, sir.
Thank you, sir.
Thank you.
Good night.
Danke.
Absolute legend.
Dankeschön.
Bye, sir.
Dankeschön.
Love you, sir. Adios.
Take care.
Bye.
Bye-bye.
Pava.
Sir's gonna grab a martini.
Right, you guys need to chill out with it.
It's so laggy.
Bravo 6 days old.
Has he left?
No, actually, it's there.
Yeah.
Wait,
Oh,
wait. Hi.
oh, I missed the last bit.
Hi, Kai.
You alright?
You alright?
Yeah, I'm alright. I'm alright.
Sound like you're in the kitchen.
Yeah, I am actually.
What are you making? Can you make noodles?
I'll make some carbonara in a minute.
Carbonara. Very nice.
Yes, sir.
Tyler, yeah? Tyler Pitt.
No.
Where are you?
Parkwood.
Oh, come on. I've seen a bit.
See ya.
Hi, you peanut.
Huh?
Oh, you peanut.
Hey, is that Kamsi?
Alright,
Your
what
breath
you...
stinks.
Alright, what
Like,
you...
Kamsi, don't even chat to me, yeah?
Yeah, Kamsi, your breath stinks.
Kamsi, you
Alright,
stink.
who invited you? I go back-
Kamsi,
I-
you stink.
Kamsi,
I
your
go back
chewing
to
gum
the
is
film.
60p, bro.
Your room's poster is trash.
I
I'm
go back
tapping.
to
I
the
said he's
film,
nice just because I got invited in there.
Huh?
With the slander, bro.
Kamsi,
Yeah,
Kamsi,
that's
just
my
because
name.
you brush your teeth with tuna chunks.
I'm so
Bro, shut up, man.
What's
You know
happening?
you had to get implants because you lost all your teeth when I knocked you out.
what?
Oh! I said you half of my teeth, you know.
What, the ones you bought, yeah? Come.
Come acting like I'm a uni student able to have splashed out a full set of implants.
Right, it's fine. I know you loaded and that. You can buy that, but it's cool, bro. You don't need to, like...
Alright, I'm going. Calm down, time.
Yeah, I'm gonna go crash your kitchen, yeah, in a bit.
Kamsi, Pava wants to say hi.
Why?
Okay, no shit. Okay, bye.
Oh my god, he's getting raped.
Bye, Kamsi.
In a bit, bro. Tom? Tom, I know you're there. I can see your freaking... Wait.